Right, I'm going to have a look at a more kind of general Macaulay's method. I jumped in there with an example, and what I'm going to do is just do a very simple UDL with no forces on it, and we'll put no figures in it either, and we'll just come up with a kind of general equation. Okay. Right, we've got a beam, a UDL. It has a load of W per metre, and it has a total length of L, and we're going to take a section cut down there at distance X. So the first thing we do, and remember, right, so let's have a wee recap. So d2y dx squared equals m over ei, and dy by dx gives us a slope, and which is kind of like, and the deflection is going to equal y. So, right, now the first thing we do is find out the reactions at A and B. Reaction at A, y, and B, y, is the total length times the load on that, and because this is balanced, this is going to be evenly distributed. The total load is W times L, is the total load on the beam, WL, and we're going to divide that by 2 because it's symmetrical, and this gives us reactions here and here. Now the next thing we need to do is work out the moment here, and again positive, negative. Therefore the moment x is going to equal, this is positive, pushing it round this way, that's going to be omega L over 2 times the distance x from it, that's positive. Now the next moment is going to be this one, the middle of the UDL, well, from this point to this point, x over 2 then, and this is going to be negative, and so that's going to be the load times this length x, similar to what we did before, and then you multiply it again by this x divided by 2, because that's the amount per length and this is the actual length, if that makes sense. That's the load over the whole from there to there, and if we're looking for the centre point, we multiply it by how long we're looking across there, and this is this part here. See where we're looking at this point, that would be like 3 over 2, 3 times x over 2, something like that. Or this point, it would be x over 4. Right, now all we need to do is integrate this bit twice and multiply it by 1 over ei. We'll integrate it once, multiply it by 1 over ei, that will give us the slope, integrate it again to get y, gives us the deflection. So we want to integrate this function here to get the slope. So let's see now, we're going to end up with dy by dx 1 over e to I, and that. And we can take this omega L out. What the f... So I thought I could hear one of my kids crying there. I think it was a telly or something. Right. So where are we? And minus the load and 2x cubed, oh, squared over 2, wasn't it? Yeah, that's right. See, that's going to be x cubed over 2 times 3. And, sorry, what am I doing? No, sorry. I'm getting ahead of myself. This is just going to be, that is about, aye, so sorry, so that's going to be 2 minus omega, and this was x squared, so that's going to be x to the 3 over, there we go, x to the 3, and that'll be over 2 times 3. And this is, so that's us got our, I'll tidy that up a little bit. Let's see, omega L x squared over 4 minus omega x cubed over 6. There we go. Plus c. Oops, that would have to be like that then, if I was going to write it like that. I can still hear some crying or screaming. It must be coming from another garden. Well, can't hear anything now, strange. And of course equation 1, that's your slope. Then again, we just integrate it again to get our y. Can you see that? Right. So that'll go up to 3, so that'll be 4 times 3, and x to the 4, and 6 times 4, plus c1x plus c2, equals equation 2. Excellent. Well, you can see that. That'll be no problem to you guys, I'm sure. Right, now, the boundary conditions again, remember, at this point here, see for this beam, mind you, the other one had various loads, and this one here, what you'll find is at this point, the slope is going to equal 0, because it's flat at this point, and then you've got your maximum. Right, and our deflection x equals 0, so the deflection equals 0, but at this point x equals the length and the deflection equals 0. So we use that again to find this here. Now, and if we just plug in to the equation here, just to make sure this disappears, you see e y is going to equal this value. If you put 0 into there, see we use this one, this these bounds, sorry, we're going to use x equals 0 and y equals 0 for this first part. So this term is going to be 0. This term here is going to be 0 minus 0 plus 0 plus C2. So again, C2 is going to equal 0. Oops, can you see that there? Right. And then for our deflection equation, from equation 2 is going to equal 1 over AI. Can you see that there? Times, where are we? There we go, that's it. Omega that's the load, sorry, length x cubed over 12, that is, minus the load times x to the 4 over 24. That was right, because it was 6 times 4 plus c1x, because the c2 part is 0. Now we plug in the next boundary conditions into this, where it was deflection is 0 again when x equals L. Right? Move that back up here, just to make it a bit more simple. It's going to equal omega L x 3 over 12 minus, oh I keep saying omega, I mean the load, over 24 plus C1x, and then we substitute L for this, which is going to be omega L times L to the 3 over 12 minus omega L L to the 4 over 24 plus C1L. So once we gather up everything together, we're going to get 0 equals omega L 4, because that's going to be a 4 divided by, right, what you're going to get here is 2, because you're going to have to have the same denominator here, so you have to double this to get the same denominator. Omega L to the 4 over 24 plus C1L, and that actually just leaves minus, because that's 2 load times the length to the 4 minus 1 times the load, so that is going to give you plus omega L to the 4 over 24 plus C1L, and then rearranging that, C1L over load, that'll be minus, actually, because we're putting this across the other side, 4 over 24, divide through by the L's, so C1 is going to equal minus the load, not omega as I keep saying, divided by 24, and C2 equals 0 there. Just move that up there, I don't know if you could see that in the last bit. So this C1, wait a second darling. So then we just put these into the equation here. I'm not speaking to you, darling. And what was that, equation 1 again, what was that again? So it was the slope equal to 1 over EI into load length squared over 4 minus load, yeah, oh sorry, that's wrong, that was x squared, sorry, minus the load times x cubed over 6, well plus, it's going to be plus this here minus load times length cubed over that. And that is our equation for slope. We could tidy it up a little bit more, I suppose. You could just multiply through by this, so that would be the load length x squared over 4 EI, and minus load x cubed over 6ei minus the load times the length cubed over 24ei. So that's like your amended equation 1 for your slope. Can you see that? Can you see that there? Sorry. I've just multiplied through with the EI and tidied this up a little bit. And then equation B for your slope. Again, you just get our equation 2 and you just put the figures into that. When we want to get deflection here again, we just put this back into the equation 2. Can you see that? Right. That was y. Just to get our deflection. Oh. Let's works out at omega, and I'm just going to multiply through omega L x cubed over 12ei. Remember that from the last one, that's been integrated, minus the load times x over 4 24ei minus omega, sorry, load times the length cubed times x. That's our C1 part. 24 ei. And remember that on the second integration, to get y, it was C1 times x. So that's where this is coming from, if you're wondering. Now you can solve these equations down even further using algebra, and we can see, the thing is, you get loads of different beams set out in different ways. You might have a cantilever, I suppose, or what we did earlier, the UDL, 2 fixed points plus another couple of loads on it. That there was kind of individual, not very well drawn. That was a kind of individual equations we made to suit that particular example, where if what we'll look at now, if you've got a simply supported beam and we know certain boundary conditions, see that just your UDL, we know that at the midpoint L over 2, halfway between A and B there, that the slope is going to equal 0. So simply to find, so people have worked all these out already. It's kind of like the second moment of area, where you can just look at a shape and it's already been figured out for you. Just look at a table. I'll see if I've got one here, but people have worked these out for different various beam setups, so you don't have to kind of work it all out. And if you have an example that you think will suit or will fit into one of these equations that's already been designed or created, so you don't have to go through all the kind of rigmarole of using Macaulay's methods, because it's actually been done for you. Obviously the tutorials we were doing, you have to make the Macaulay's method, but it is handy to know when you're an engineer, whenever you're wanting to look at a certain type of beam, if the material's already there, you might as well use it. But for instance, to give you an example, the deflection, this equation up here, if you substitute L over 2 into X there, we're not really boring into the algebra, but what happens is you end up with your deflection, or Y, equals minus 5 the load times the length to say 4, 3, 4, AI. So looking at this here's one here. So if you look, so you've got a distributed load there, right? And if we're looking at what we worked out there, for at the centre, the deflection at the centre, it actually gives you a coefficient here. And what that is if you look at that closely, you'll see that's 5,384, and that is a UDL with a distributed load. And we're looking at the deflection coefficient. What that means is, say this is your kind of deflection, and this coefficient here is determined by how the load is distributed along the beam, and it can come in various forms. Like this one here, if that was just a point load, you'd put 1/48 in front of that type of thing, and you get your slope, whatever you've worked out for your slope. Let's see, it's got your slope equation there, see, and it's got your maximum deflection and maximum bending moment at this point. But that's so, and that is handy as well, I suppose. So it gives you your slope coefficient, and these are at the ends of the particular beam. At the ends, this is at the free end, this is the slope at the load. It sort of describes, and if you have this one here is slightly more complex. Let's see, you've got ones that are propped up as well, and so you look at the beam and the loading on it, and then you try and fit or suit it to one of these. And if you can't do that, you'll have to make your own one up using Macualay's method. Okay, I hope that makes sense for that so far. And for this type of beam, you find the deflections there will be, the slope there, they will be equal. But obviously, to find the slope at say x equals 0, you would just plug in x equals 0 into equation 1, into equation 1. And if we do that, that would be, what was it, load length of that 0 cubed for EI minus the load times 0 cubed over 6 minus the load times the length for EI. Therefore they'll evaporate into thin air. And you're going to get a load times the length cubed over 24 EI. And this would only be the slope at x equals 0. And just for this one actually just works out that they will be the same. But the thing is, to work out the slope there, remember that would be your x equals 0 and your slope, the length equals 0. Where did I say? Sorry, I mean you just substitute x equals L at this point. I meant to say that's, I was thinking about deflection there, that's your slope. You get your maximum slope at x equals 0 and x equals L. So it might be different depending, but if you use a Macualay's method it will be different, because purely by the fact that you're using Macualay's means there isn't a set out answer for it. So and these will give you, so in there you'll get your end slopes and your deflection. Okay, I hope that makes sense. Right, and remember that was actually just at the midpoint there. So that's a deflection at midpoint. And this is the deflection, sorry, the slope at the ends, the end at x equals 0 or x equals 0, but it will vary obviously. Right, well that's making sense. This was all revolutionary in the 19th century actually. When the Eiffel Tower was built, some engineers didn't think it would actually stay up because they didn't quite understand this Macualay's method and all that, and Eiffel figured out it was very useful, and he used that in his design basically. Whereas, as I'm saying, engineers, a lot of them thought, oh, this isn't going to work, but it did. The maths proves it. Maths never lies. But thanks for listening again, and I'll send you more stuff as soon as, okay? Take it easy, bye.